All right, here's the last one of this and then the last problem. So David has a box which is sliding down the wall at constant speed. So there's the box, and constant speed means F net is 0. So we're going to take a look. It's 3 kilograms. I'm going to draw FG. Whoa. FG is going to be 3 times 10, which is 30. There you go. Then I'm going to draw his push, because that's our given, and that's going this way. Okay, and F push is going to be 55. Oh, God. My cat and dog are fighting right now, so I hope you can't hear it. Shh. Sassy. No. Okay, guys, sorry. Can you hear that? I don't know if you guys can hear that. Okay. But if you can, don't worry, the cat's under the bed. It's fine. All right. The other two forces we have, we're going to have friction, which is opposing the motion, and this says it's sliding down, so friction's going to point up. And then we also have normal force, and normal force is perpendicular to the surface. We're talking about the box here, so the surface is the wall, so it'll point out at David. So I'm going to put in here that this is our force of friction. That's equal to 30. And then down here, we're going to put in this is our normal force. That equals 55 newtons. Don't worry, I'll fix this up for us so we can see it. There we go. Okay, so there's your free body diagram. I'm gonna fix it a little bit because it looks kind of wonky. This looks really wonky to me. I'm gonna try and even out those arrows. So this is probably about even. This needs to get longer. Okay, I feel better about that. All right, that's that one. And now we'll go to the last one. So we've got when how. He's pushing up an incline. I know you guys love inclines. As shown, and it wants to know what's the box's KE at the higher point if he pushes with 217 and include a free body diagram. So here we go, free body diagram in it already. We're going to start with force of gravity, which is given, and I'm going to do component form again. So those two components. So this is FGX. That equals 108 newtons. And I should have moved this over. Whatever. This one down here is FGY. That's equal to 258 newtons. Okay. Now, if you look, because we're going to keep going with the rest of our free body diagram, we got to look at the information we're given. So we're given that it starts at rest and then it's not at rest. So we know that this is not a F net equals 0 situation. We also have over here mu sliding, which is mu kinetic, and mu static. And so we're going to use mu sliding to get force of friction. But in order to do that, we need to get normal force and finish our free body diagram. So this is moving up this way. We're going to include Wenhow's pushing force. So that's his 217. That's where this comes from. Made that a little bit too long because it should definitely be shorter than the force grabbing point down. And then I need to also include up here, this is going to be normal force. And normal force is going to be equal to force of gravity pulling it down because the box is moving up the ramp. It's not bouncing off the ramp up into space and then landing again. It's moving, if you think of this as the x-axis and this as the y-axis, it's moving on the x-axis but not on the y-axis. So we've got to put that normal force for this. Oh no. The cat and the dog aren't fighting anymore. All right, we've got normal force is 258 to balance that out. Over here, I've just got to finish up that when how. I feel like Oh, that when how pushes with 217. And then the last thing I have to do, I have to include friction. So we can do friction now. Whoa. We need to do a calculation. So the force of friction is equal to, oh, I don't know what the character mu, how to type it. Well, I'll just type mu. Mu. We're going back up. Mu times normal force. Okay. So our force of friction is going to be equal to 0.26, because we're using kinetic, times, oh my god, normal force, 258. I'm doing the math, guys. All right, it's 67.08. I guess. I don't really remember that number, but I'm just going to go with it. I'm pretty sure about it. Okay, so there's our, oh geez, you guys. There's our force of friction, and it is 67.08 newtons. Okay, now there's our free body diagram. Now what we're going to do is we're going to figure out what the box's KE is at the higher point shown. So the KE here. And so the movement of the box is up the ramp. So the three, what's it called? The three forces doing work are these three that I just circled. So let's go to here. All right, so we're going to do a good old E1 plus W equals E2. And at the first point, there's no energy. It's at rest, and it doesn't have any GPE. So we can do work of gravity plus work of friction plus work of when how. And that's going to be equal to the KE at 0.2, but not the GPE. Because I'm using the work of gravity, I don't include the GPE. So, oh boy. Oh. So now let's get to calculating. So the work of gravity, well, first of all, this is going up the ramp, and gravity and friction are pointing down the ramp. So they're both doing negative work. So make sure 0 plus work of gravity is a negative 108 times the D, which is 3.9, plus the work of friction is going to be a negative 67.08, again times the 3.90. I think, did I say 3.09? And then when how is going to be doing positive work, so 217 times the 3.9, and that's all going to be equal to KE2. Now, I don't have my calculator, but I should have been prepared for this moment. We've got a calculator on here, right? I don't know if you guys can actually see what I'm doing right now, but that's okay. So when I calculate this, so I've got 3.9 times the weight. That gives me a negative 421.2. The 67.08 times the 3.9 gives me 261.62, so that's a negative. And then the 217 times 3.09, nope, 3.90 is 846.3. Okay, so we're going to add those all up together. And let's see what we get. I get 163.48, which again, I don't really remember getting, but I feel good about it. All right, look, just in time. We're good.